Does it work?
It works.
Yeah.
Thank you.
Good. So you might notice that the title here is a little bit different from what I promised initially. Because after I submitted the abstract, they invited me to give a bigger presentation after the coffee break. So I invite you to come there, and there you will see a bit more of what I promised initially for this session. Instead, I decided to look a bit more not at the entire boundary layer dynamics during these events, but focus a bit on what we observe over different green spaces in the Paris region during the heat events of 2022. I acknowledge, of course, a large range of people that contribute to these observations in the Paris region, and you will also hear more about this in the other presentation. So, as a background, I just want to say that in Paris, like in many other regions of the world, we now have long measurement series that tell us a bit about the trends that we observe. We have reduction, we see in a reduction in cloud cover, an increase in shortwave radiation accordingly, and of course a trend to higher temperatures. And in Paris, we are lucky that the local authorities are responding very nicely and try to also adapt to these higher temperatures and protect the urban inhabitants. Because, I mean, they are a bit forced to, because we see a large number of excess mortality in Paris due to these strong heat conditions. So, for example, the Paris city and also the Paris region, they try to cool down the city, and one of the major methods that they use is to increase green infrastructure. For example, the mayor of Paris has just announced this year that they aim to increase the park size, the park area in the city quite substantially in the upcoming years. So the idea of our study is that we wanted to see what is the cooling potential of different green spaces that we have in the dense city of Paris. For this, we're using measurements conducted in the region. We have now a very dense measurement network, including surface station data, profiling, fluxes, all sorts of different observations. Here in this presentation, I'm mainly focusing on air temperature measured in the city and outside at a rural site, and also we use some data from the Eiffel Tower at an elevated location, and then I'm using also some mixing information that we get from the Doppler LiDAR that is operated in the city center. The main focus is in this presentation on profile observations that we gather with lightweight radiosondes. So these are systems that can be operated pretty easily also within the city, in urban locations, in different parks. And we made some intensive observations during the heat waves last year, both in urban locations, in medium-sized park, and also in two big wood areas of Paris. And this happened during two strong heat events that we had in June and July last year. So to focus a bit on the July heat wave period, I plot you here the air temperatures that we observe in the city center, in the urban parks is the yellow, and then the green is the rural temperatures. And on the bottom you find the heat island intensity in green. We see that there's, of course, stronger differences between the urban environment and the rural side compared to the difference between the urban environment and the parks. But what I want to point out more is that we have quite some night-to-night variability. So within this week, we had pretty much no cloud cover, and the conditions appeared similar in the first glance. However, for example, on this night, there was stronger winds, so we see a reduction in heat island intensity. But what we also interested in is to see what makes the difference between medium cooling difference and strong cooling difference of these urban green spaces. One aspect that we find here is that in the night with the strongest temperature differences, we have very strong thermal stratification. So the air temperature that is observed at the 290-meter measurement site at the Eiffel Tower is similar or even higher compared to the measurements at the 2-meter level. So in these nights, we have very strong stratification observed in the urban setting. Another means that we can use to quantify the stability of the atmosphere is the mixing that we observe with the Doppler LiDAR. Here you see a time series of the vertical velocity variance calculated at the first LiDAR gate. So this is at 240 meters above the Earth's surface. And again, we see that there's pretty much no mixing reported in the nights when we have this strong stratification and the strong contrast between the urban and park temperatures. So now let's look at what we can observe with these temperature profiles that are observed with the light wave radiosondes. We did measurements in, as I said, in urban settings. So we here in the background shading is indicating the location. And the green background are the woods where we have a large vegetated area, and then in comparison the parks. And yeah, there's a lot of information there. We can't go into much detail, but this is just to show you. Okay, we did on most nights we did 3 observations at the peak heat time and 18 local time, and then every 4 hours until 2 a.m. in the morning. And of course, we can see the cooling from one profile to the other, but we also start to see the vertical structure when the inversions are forming from the ground up. Okay, I uploaded a different version of this presentation and it seems not to have made it. Where I sorted out this mess for you into different figures. Sorry about that. What I wanted to show you here is that if we combine the information from all the soundings that we made over the summer, comparing the urban, the parks, and the wooded areas, we can start to see some structural differences in the stratification. So in the red, if you would see the updated version, you would be able to see that on most nights we have neutral stratification conditions, because of course we have the urban area maintaining the buoyancy, maintaining the heat, and there's always some level of exchange vertically. Whereas if we go to the park areas, the inversions start to form. We have the cooling from the surface that is stabilizing the atmosphere from below. And then, of course, the green spaces, they cool more compared to the parks. I made some calculations that I was going to show you, so that in general we have on average up to 2-degree cooling, but in extreme nights up to 4-degree cooling if we're in these medium-sized parks. There's one outlier where we have very stable stratification generally in the atmosphere. And what we wanted to understand now is, okay, we see, as expected, stronger cooling in the large vegetated areas. This is not surprising, but usually we quantify this based on 2-meter temperature observations. And what we are now able to do is analyze also the vertical structure, so the depth of this cool layer. And we find that in the parks, the cool layer that is forming over the green space, it extends to about 25 to 50 meters, whereas over the woods it's about 100 or maybe 150 meter maximum. So this helps us to calculate the volume of cool air over the green space that is remaining, that is forming there during the night. We can summarize this cooling effect now. So, but what we also wanted to understand is what drives the deviation between the nights. So, in extreme cases, the wooded areas cool by up to 7 or 8 degrees, but there's also night that it only cools like 1 degree. So, of course, we can go back to the idea of stability quantification, and I showed you before that we can use this mixing indicator at the first LiDAR gate to quantify the state of the mixing, the stability in the atmosphere. And this is what we see here on the x-axis. If we go to this side of the figure, we have more mixing, more unstable conditions, and in this case, of course, the cool air of the park and the warm air of the urban environment is mixed effectively, maybe also with the rural air, so we see less contrast. But if we go to the other end of the figure, where we have the very low mixing, we start to see the spread. And in the urban settings, there's still not much cooling. We have the maintained heat. If we go to parks, they start to cool more effectively compared to woods, of course. This is a stronger effect. So we can say that with this mixing as an indicator, we can understand the spread of these cooling events in the parks. So to conclude, we can see that in summer 2022, we had clear cloud-free conditions that occurred with a range of thermal stratifications. And we see that the vertical mixing over the city is a very good indicator to understand this stratification near the ground. We can see that the cooling effect of the urban green spaces is really also depends on the stability regimes, because under low mixing conditions, the surface radiative cooling really dominates, and in these cases we can see that the medium-sized park cooled by up to 4 and the woods by up to 8 degrees, whereas the layer that is being cooled is about double the size for the large woods. Of course, as expected, if we have a lot of mixing and turbulent conditions, we see less contrast both between the city and the rural background, but also compared to the when we look at the intra-urban variation between the park and the build-up areas. And so with this data set, what we now want to understand is also the exchange between the rural air and the urban air, how this influences the mixing and the cooling from above, but also in terms of using green spaces to cool the urban environment. This raised the question that, okay, we want to lower the heat risk in the city, but we can also demonstrate that when we most need it, when we have the highest heat island, when we have the highest temperature, the cool air stays where it is. So it is very cold. I mean, I've been there at 3 a.m. in the morning. It's so cold. You go out of the park, it's 8-degree warmer. It's crazy. So what does it mean? We need to bring the people into the park at night, or we need to take the cool air out of the park and design it in a way that it can flow out or, you know, exchange with the heat environment around us. Thank you.
All right, thank you for this talk. We'll start down here with Scott.
I have a very technical question.
Yes.
If you can't answer, we can take it offline. The dream of the Doppler liner fascinates me.
Yes.
So over what time period